Welcome to lesson number 3. We're going to be looking at quadratic functions again, but this time we're looking at what happens when we add another parameter on our graphs, and the a value is what we're going to be looking at. So first of all, we wanted to again look at, actually this is a different graph. We're looking at f of x is equal to x minus 2 squared. So not looking at x squared today, but we want to write an equation which represents each of the following. So y is equal to 2 times f of x. So 2 times f of x would look like this. Y is equal to 2 times x minus 2 squared. And also this equation, y equals 1/2 f of x. This would be y is equal to 1/2 x minus 2 squared. And then we want to use a calculator to show what each of these graphs look like. So x minus 2 squared, and actually before I'll put my original graph in, and then we're going to see what happens to each of our graphs as we add that a value in there. So x minus 2 squared and 1/2 x minus 2 squared. So here's our first graph, we have our second graph, and our third graph. So this one that's inside, I'll turn off that third graph. So here's our original, here's our second graph. This is 2 times x minus 2 squared. And so I'm just going to do very crude drawings, so something like that. That was this graph here. If I compare these two graphs, let's see what happens. So compared to the graph of y equals f of x, the number 2 in the graph of y equals 2 f of x results in a vertical expansion or compression by a factor of, well, here we have a vertical expansion. So all my y values actually move up. And so because it's moving up, it looks like it's getting a little bit skinnier. All right, and this happens by a factor of 2. So the y-intercept of the graph of y is equal to 2 f of x is going to be doubled. And so if I look at where my y-intercept was here, it was at 1, 2, 3. If I zoom in, option 2, I'm going to zoom in on my y-intercepts. So that's my original and my new one. So 1, 2, or sorry, no, that's at 3. And my original, or sorry, my new one is going to be up higher. And I actually zoomed in too far. So standard. So if I go up to my new line, it's around there. My new one is going to be here at 6. So complete the following by circling the correct choice and filling the blank compared to the graph of y equals f of x, the number of 1/2 in the graph. If we examine our other graph and what happens to our, so I'm going to turn off this one, turn on this one. And I'm going to have to zoom out here. So if we look at our new graph, we've gone half. So when we were at 3, now we're at 1.5. So this resulted, so compared to the graph, the number 1/2 in the graph of 1/2 f of x results in a vertical again, but vertical compression by a factor of 1/2. So the y-intercept of the graph of y is equal to 1/2 f of x is going to be half the y-intercept of the graph of y equals f of x. So now we're going to write an equation which represents x squared. Write an equation which represents negative f of x. So this would be y is equal to negative x squared. And we have y equals negative 2x squared. Now we want to use a graphing calculator, and we'll want to graph each of these. So first of all, negative x squared. If I graph this, here's my, let's get my original. My original is x squared. If I graph this, there's x squared. Negative x squared, all it's done is it's reflected it in the x-axis, right? So it's taken this graph and flipped it upside down when I put a negative in front of that function. So all these values are going to be reflected across the x-axis. Something like this. But my vertex remains the same at 0 and 0. Now if I, so I'm going to turn that off. And now I have negative 2x squared. So my original graph and my new graph. So notice how this graph looks skinnier, and that's because all the y values have been stretched upwards. And so this is a vertical expansion. So my vertical expansion, these values that were at 1 are now going to be up here at 2. This value at 0, 0 is going to be the same. The values that were at 4 are now going to be up here at 8. So 5, 6, 7, 8. This is what my graph is going to now look like. So let's complete this chart in relation to what's going on in this graph. So the function represented here was y is equal to negative x squared. The vertex remained at 0 and 0. Now, however, my original graph had a minimum value. That was the lowest value of y. But now we have a maximum value and a maximum value of 0. If I split this graph in half, my axis of symmetry is equal to 0. And we had a reflection with that negative sign in the x-axis. With this graph, and it's this graph I will highlight, that was negative 2x squared. And so y was equal to negative 2x squared. Our vertex remained the same. It is still 0, 0. That didn't move at all. We still have a maximum value at 0, and we still have an equation of x equals 0 for our axis of symmetry. But we had two things happen. First of all, we had a reflection in the x-axis, but we also had a vertical stretch. So all my y values were stretched out vertically by a factor of 2. With this example here, just if I have a parameter a that's changed or added to my graph, that's going to be ax squared, where a has to equal, or sorry, be less than or equal to, or it has to be less than 0. My vertex will be 0, 0. My maximum point will be 0. And my axis of symmetry will also be 0. This would result in a reflection if it's less than 0 in the x-axis, and a vertical stretch by a factor of whatever that a value is.